Okay. Hello guys, in today's video we will be finding a potential using the method of multiple expansion, and we will be going through the problem 3.28 in the textbook. It's one of my homework problems, and that particular problem refers to the section 3.41. I will be going through this problem, explaining everything that I needed to explain to myself when solving this, because it wasn't that easy, even though it seems easy, but the problem was mainly in figuring out the relationships between Cartesian and spherical coordinates, because both are involved. And so let's just go straight into it. Okay, our task is to find the first three terms in the expansion. We can use the formula 3.95 in the textbook as our starting point, because it has already been derived for us, and we then are asked to find the first three terms in that expansion for n equals 0, 1, and 2. So let's write that down. Okay, that's how this looks like. Before moving on, I would like to draw a picture, a diagram that will describe our problem, so that we have an easier time to figure out what we need. Okay, drawing our Cartesian coordinates. So there is a ring of charge, well, sort of a ring, situated at the origin. And then there is some field point P, where the position vector r is this, and the theta is our polar angle. Also, we have a radius r, as well as our r prime. So the vector r prime is the vector describing the position of the little element of charge dq. dq prime, that is a source of our electric field and also the potential. Since we will be integrating over this ring to count all of the little dq's, it is important to specify the angle we will be integrating over, which is phi prime. Okay, I think it looks pretty good. Also, there is a line charge density. And I think it's important to specify the angle alpha that is usually comes up in the expansion. And this is the angle between the vector r and r hat. Okay. Oh, and by the way, in this setup, it doesn't pertain to this problem in particular, but I thought I will just mention this distance here will be our curly r that is very often used in the electrostatics problems, and that is the distance from the source point to the field point, but it's not used in this problem because we need these two vectors, and then we need this vector, this angle alpha, to be able to do our calculations for each term in the expansion. Okay, now that we've got this, let's look a little bit closer on what each term in this expansion looks like. If we look here, let's say we look at the first term. We know that this is a ring of charge with the line charge density. These integrals are all in terms of the volume charge density and the volumes. This is a very general case, which can be written for a surface charge densities or a line charge densities, just as we have here. So then this here becomes just lambda, and it's uniform, so it's constant and can be taken out of the integral. So is this here, it's just lambda. Then our r prime is our radius. So this term then becomes r squared. And then all these d taus then become just dl primes, because we will be dealing with the line integrals. Like each of these integrals is actually a line integral. So d tau is actually dl prime. And if you recall how to calculate the arc length, so the arc length can be found as radius times the angle, and in this case it will be, so our dl will then become simply r d phi prime, because we're integrating over this circle, and as the phi prime angle changes, we count up all the little dl's. So the dl's will be replaced by this. Only term left that we are not exactly sure how to interpret in these integrals is our cos alpha. And the cos alpha, remember, I show you in the picture here on the page 154. Remember that alpha is the angle between r and r prime, so the integrals depend on the direction to the field point. It seems like to get the cos alpha expressed in terms of our angles phi and theta pertaining to the spherical coordinates, we would need to take a dot product between the vector r prime and r. Okay, so the cos alpha, as I just showed, depends on the vectors r prime and r, and it's the angle between them. And we can get cos alpha from the dot product definition. Recall that r dot r prime, like, or any dot product between the two vectors, is defined as their magnitudes times the cos alpha, and the alpha is the angle between the two. In our problem, we actually can see that, well, the magnitude of the vector r, which is the position vector to the field point, is just r, and the r prime magnitude is our big R, and then cos alpha. Okay, so on this side we know these two quantities. We are looking to get cos alpha, and so the only thing left to figure out what it is the dot product, the actual dot product. And to do that, we would somehow need to express this vector in terms of angles phi prime and theta. And I have prepared a few diagrams here helping us to do that. So we are looking for these two vectors. Let's start with the r prime because it's the simplest of the two. And if you look at this picture, I hope you can see it. Okay, so if you look at this diagram, I got the base diagram from the Griffiths textbook, from the spherical coordinate section. So if you're curious, you can get it, you can look it up there, and then I made some drawings on top. So we are looking to get this vector here, which is our r hat. Yeah, this is our r hat. Okay, so for solving this problem, the part on figuring out the r and r prime expressions took me the longest. And then once I got that, and once I got how these two vectors connect to what we're actually looking to find, it got really clear from that point on. And so because it was so difficult for me to figure out at first, I decided to share this as well. It might be very obvious for some of you guys, but it wasn't really obvious for me because math is my weakest point, and it's kind of hinders me to go any faster than I can go. And maybe that's one of the reasons why I'm not getting the grades I want, because math is really slowing me down. Anyways, so this vector, if we look at this, is just a sum of this vector and this vector. and we are like only confined to the xy plane. So the component that describes this vector along the x-axis will be big R cos phi prime, just from the right-angled triangle and the standard sine and cosine definitions. And this side here is defined, will be R sine phi prime. Yeah, this here and this here is more general definition. It will become useful once we will be looking to find the expression for the vector R. And so the final expression for our R prime looks then like this. It's just a vector sum of these two components. So that one was easy. And if we will look to find vector R, this then looks like this. Okay, here there was one subtle point to understand, is that when we are trying to express vector R in terms of the three components along the x and y and z axis, that angle phi is not the same angle phi that we used to describe this vector. Because the R prime is really, the magnitude of R prime is really just R. Like if we are integrating around the circle as in our problem, this is just a general picture of the spherical coordinates, how it's defined. But in our particular problem, remember we have this circle of line charge. And so our R is fixed. And if we're just going around this line, the theta angle is always the same as well. And so this phi, the phi prime, just describes this vector. It belongs to this vector only. If we go more general, to describe any point P in space, like you can imagine that this point could be up here or down here, and so the theta will change, and the projection of this vector on the xy plane will change as well. So this length is no longer R, and also the direction also changes all the time. So this phi is different from d phi prime. And then our components look like this, and the final expression is then this, where we take each component along each direction and put it into a vector sum. And now when we take the dot product of these two vectors, we get the following. Okay, getting our normal dot product. So we just, it's a product of each term and then the sum of each products. If we multiply this term by this term, x hat dot x hat is just equals 1, so it disappears. And similarly for the other terms. Okay, so this one is kind of out by itself. There is no z component on the r hat vector, so it's the dot product between these two components will be 0. And then some rearranging is then gives us then okay. And so, okay, I'm just going to rewrite this here, down here, so that it's easier to see. Okay, looking at this expression and this, we can compare and then conclude that this portion here is our cos alpha. And so cos alpha, I will just write it out separately. So now that we have this, it's pretty straightforward to get each of the terms, each of the terms in this expansion. We'll just take our cos alpha, substitute in here. We know our lambda is constant. We know what the dl prime is. it's r d phi prime. And so we will compute each integral and get our first three terms in the expansion. Okay, so for the term 1, okay, looking here, it's 1 over r, and it's then 4 pi epsilon 0, 1 over r, lambda r d phi prime. And when we are integrating over the phi prime angle, we're just going around the circle, so the integration bounds will be from 0 to 2 pi. And so the first integral is really simple, d phi prime, which is just 2 pi, and then okay, now we can cancel the pi's and the 2's cancel, and so we get lambda r over 2 epsilon 0 r, and that's our final V1. Okay, so that's the first term. Now the second term, looking up in the expansion, second term looks like this. You can tell I'm being extra explicit with what I do and what I write. It's just because I don't want to make any algebra mistakes, and also to make sure that the grader knows exactly where everything came from, because really the last homework was in this format, was extra explicit, and I got a 99% on my homework for the first time in this class. So I'm taking my time to write everything very explicitly. Okay, our cos alpha is a little bit more involved. Okay, then our lambda r d phi prime. Okay, that's our integral for the second term. It looks a bit intimidating at first, but in fact it's also not very difficult. Actually, not at all. Okay, let's do some rearranging and taking out some constants. R is constant, lambda is constant. This r is constant, of course, too. And the sine theta can also be treated as constant because we are integrating with respect to phi prime. Therefore, this cos phi and this sine phi are also constants in this case for this integral. And so we have let's rewrite this one more time and separating the integrals. Okay, when separating this integral into two integrals, I will be taking cos phi and sine phi out of the integral because, as I mentioned earlier, it's constant with respect to d phi prime. Okay, now let's think a little bit. We have cos phi and we have sine phi. When we integrate this integral here, it's going to be sine phi prime from 0 to 2 pi, right? If we do this calculation, it's actually 0, right? Because sine of 0 is 0, sine of 2 pi is 0, so 0 minus 0 gives us 0. So this whole term goes to 0. And this integral here, it's going to be minus cos phi prime from 0 to 2 pi. But this also is going to be 0 because it's minus 1. We're going to get minus 1 plus 1, so also 0. And the whole thing is then just 0 because this whole bracket turns out to be 0. So then the potential, the second term in the potential expansion is then 0. Okay, awesome. Now we have found second term, and the third term is a little bit more involved. It's not super difficult either, but there's just a lot more writing. Okay, now that we've got our expression for the third term and expansion, I think what I'm going to do, I'm just going to take this bracket here and split it into two integrals and solve each integral separately, put them back together to simplify the final expression. So the first integral is going to be this part integrated over the phi prime. And then the second one is the very easy one. It's basically just equals 2 pi. When we integrate integral of 1 d phi prime, we get 2 pi from it. So let's do this one. Maybe I'm just going to write that the second one, let's say I2, equals minus the integral from 0 to 2 pi, 1 d phi prime, which is then just minus 2 pi. Okay, and the third, then the first integral is then 3, oh my goodness, again, cos theta, it's not cos theta, it's sine theta. 3 sine theta. Okay, it's a bit tedious, but it works. Expanding this bracket term. So here we can have 3 integrals, and I think this one will be 0. It looks very much like it because, let's see. Let's do it one by one. Here, this part is constant, can be taken out, and then we're left with cos phi prime times sine phi prime d phi prime, integrated over the period. Actually, from 0 to 2 pi, it's the whole period of any of these two functions, these two. And if you notice, cos is an even function, sine is an odd function, and the product of the two is an odd function. And if we integrate an odd function over its period, the integral is going to be 0. Because think, let's say we have sine. Yeah, so if this is 2 pi, then the contribution from this part and this part, they're going to cancel out. So that's for an odd function. Okay. And excuse me for extremely small writing here. This copy is actually my final copy of this problem, and I'm going to hand this in as my assignment, like one of the assignment problems. Here, we're left with these two integrals, and again, cos square phi and sine square phi can be taken out. And then we're left with this under the integral sign. And this can be integrated directly, of course, but I'm just going to look up this in the table. It's been very long already, and I don't want to do all this calculation. I know how to do these integrals. We just use the trig formula to convert this to the double angle, and then make some u substitutions and solve it. But we can very conveniently look it up in the integral table. And if we do that, well, let's first rewrite this expression in a neat way. So the whole thing is going to be 0. And then we get, okay. We're almost done, guys. Almost done. So putting all these values in, we get pi from here and 0 from here, because really this is just the integer values of phi prime, so the sign will always be 0 here, and it's just pi. Similarly, on the sine squared, we get okay, and again, the same thing happens here. It's just equals to pi. So then, with all of this, this first integral becomes then okay, not forgetting this here, cos square phi times pi plus sine square phi times pi. And as you can guess, if we take out the pi, cos square phi plus sine square phi equals to just 1, and then the integral is then just 3 sine theta times pi. Okay, now putting it all together, remember we had this expression for the V3. So V3 then is R3 lambda 8 pi epsilon 0 r cubed times the value of this first integral that we calculated here, I1, which is this 3 sine theta times pi minus 2 pi. Okay, then the pi's here cancel out, and we get our lambda over 8 epsilon 0 r cubed over 3 times 3 sine theta minus 2. Okay, now, well, we could leave it in this form, but I think it looks really similar to something that contains some Legendre polynomials. And more precisely, it's the P2. I believe it's the P2. Let's look at this. Here, it looks very much like this, except that instead of the x, we have... oh wait, did I leave the sine squared out? I think I missed sine squared. The square here. It's supposed to be square. When I was squaring this whole thing, it's not just this bracket here squared. It's actually like this. So the sine theta also becomes a square. Okay, let's do some changes. So it's done sine squared throughout. Oops, I just noticed it. Okay, now this expression looks similar to this, except that instead of x squared, we have sine theta squared. And also, referring back to our original multiple expansion formula, we have Legendre polynomials in terms of cos alpha and not sine. So we can try to bring it into the sine form, cos form. If we just substitute oh wait, again, I'm sorry guys. My goodness, it's very late, by the way. It's 11:41 p.m. but I was determined to get this video done, so bear with me please. So it's then 3 minus 3 cos square theta minus 2, which is then 1 minus 3 cos square theta. Okay. And if we want to make it look similar to this, we switch the terms, the places, so it's then minus 3 cos square theta minus 1. Okay, now putting that back in to the expression for our third term. Oh, and also there is a factor of 1/2 at the bottom, so I think I will take out that factor from the denominator here. So then we, like, dividing by 2, it's going to leave us with 8 epsilon 0 r cubed. Okay, and now this can be then rewritten like this. Okay, looks about right. So our final result is then, okay, and that's our last term and the expansion that we were asked to find. So that's about it. This problem took me 3 pages, not including these 2 pages here. It probably could have been done a little shorter, but I wanted to be extra explicit about everything I do and not to leave anybody guessing what I did here. As well as it was very informative for myself, I was really able to understand what's going on here, and I hope it was somewhat helpful. So thanks for watching, guys, and I'll see you next time.